Good day, everyone. This is Ricard Ebon, a BSEA student, and I'm going to report the chapter 3.5, the research tools. So, in every research project, the challenge is to validate the results using independent means. That is, the techniques that will be utilized to carry out this validation must be explicitly outlined in the research studies. So, the strongest case can be made if the experimental or numerical results can be validated against a theoretical model. If two very different independent methods yield results which are statistically identical, then it is highly likely that both tools used in the research are valid, but there's still a probability that both of these are incorrect if they have shared a common error of both methods of analysis. Some example of that is the systematic uncertainty. So the research team uses a published method of measurement. The conclusions agree with previously published work. This might be because there is a systematic error in the measurement technique which has not been identified. The net result is that both the published paper and the new results are incorrect. What methods are available to ensure that such problems are eliminated? So what are we going to tackle right now is some solution in order to eliminate that kind of problems. Experimental measurements. Standard measurement tools provide the best method of gaining reliable measurements. If alternative measurement techniques are used, then the researchers must verify their tools through a calibration procedure. So if you use an alternative techniques, the researchers must go through a calibration procedure in, in order to verify that their measurements are valid. Example of calibration procedures. First is using provided standards. That is like the standard solutions in chemical analysis, standard loads for electrical and microwave power level measurements, and etc. As the use of materials with properties that are well known. So that is the standard measurement tools because it provides reliable measurements. Next is null calibration techniques, like when you run an instrument in a blank sample. Example of it is in air or pure water. An example of it is in calibration in experiments. A new microwave vector network analyzer is delivered with a set of standard microwave loads for calibration purposes. Measurements which are made without the standard calibration procedures will be very error prone. When measuring the intrinsic impedance of a material half space at microwave frequencies, the probe should be calibrated in air and against a copper sheet or a near-perfect electric conductor at microwave frequencies. So the calibration procedure should eliminate the effect of fringing fields, cables, and connectors. A UV visible spectrophotometer uses a split beam light path. One beam is directed through a high-quality, pure solvent as a reference, and the other passes through the sample under test. In this way, the effects of temperature, frequency variations, and the optical properties of the containers or cuvettes are removed from the optical absorption measurements. So many countries have measurement accreditation authorities. Example of that is the National Association of Testing Authorities in Australia, or NATA. It is the recognized authority for validation of the equipment and measurement practices of organizations which undertake measurements on a commercial basis. So they mostly covers the engineering and the scientific test requirements. And also the International Organization for Standardization, or the ISO, they provide documents which describe standard measurement techniques. And also many national government bodies and international professional societies, they also develop and publish other standard measurement techniques to guide and encourage many researchers for the best of their research proposal and research outcomes. Next is numerical modeling. experiment so many computer codes in internet, and one of them is Flitora. Computing codes, which are based on the solution of the differential and equations, require a solution space which has finite dimensions. Example of it is finite element and finite differences methods. So one of the three is the mixed codes, differential codes, or mix of integral and differential equations. The solution space is defined by a discretized area, 2D pixels, or volume, or 3D voxels, representation of the object and its surrounding media subject to various external inputs. While the differential codes, the media surrounding the object must be included in the model, and the boundaries of the solution space must be sufficiently far away from the object to ensure that the boundaries of the solution space do not affect the area and or volume of interest, because it can affect it has a significant effect on the accuracy of the solution. That's why you need to be far. It needs to be far away from the object in order to have a boundary. While the integral codes, there is no requirement to define those boundaries to the solution space. So it is okay for the integral codes to have no boundaries. So example of that is the multiphysics computational methods. The dynamic response of a microelectromechanical or MEMS lever switch requires the solution of mechanical and electromagnetic equations. As the switch moves, the electromagnetic environment changes and the restoring phase force or on the lever changes simultaneously. The approximate solution to this problem requires a time-step re-evaluation of the next mechanical situation as the lever moves under the influence of the force. This requires repeated solutions of similar structures, which can be performed efficiently using a small perturbations in the total structure. The mechanical model and the time variation are formed using discrete steps. It is necessary to ensure that the model is valid by computing the solutions of standard models and comparing the results with theoretical calculations. So this can spot errors that are challenging to spot when looking at a model's image. Imperfect continuity between materials, boundaries, and materials qualities are frequent errors. There are also limits to the discretization, like if the segments in the model are too small, then the program can experience rounding errors. If the segments in the model are too large, then the true representation of the continuous media is lost. It is possible to construct a material barrier between two nearby nodes, with the distance between them acting as the upper bound on the spatial resolution. Changing the mesh size in the same model and running the calculations again is a recommended practice. It is very likely that the solution is correct if the solutions are almost identical. Derivations and calculations. When developing a mathematical argument based on a set of theoretical equations, it is necessary to verify the solution. This can be achieved in a number of ways. For example, if it is substitute the final equation back into the original equations to ensure that this provides a valid result. It means verifying that the final equation obtained by solving a problem satisfy the original equation or set of equations used to describe the problem. By substituting the final equation back into the original equation, one can verify that the solution obtained is valid and consistent with the problem being studied. If the solution does not satisfy the original equation, this may indicate that an error has been made. Next is check that the solution lies within the expected physical limits. So it refers to the process of verifying whether the solution obtained for a particular problem or situation is realistic and conforms to the laws of physics or other relevant constraints. Next is check the units of the result using dimensional analysis. It means verifying the units of the calculated results to ensure they are consistent with the units of the input parameters and the physical being measured. Checking the units of the result using dimensional analysis is a crucial step in scientific and engineering calculations, as it helps to identify errors and ensure that the results are physically meaningful. Next is check the validity of the solution using mathematical programs. Example of it is MATLAB provides symbolic methods of solution for differential and integration equations. So that refers to the use of specialized software or programming tools to verify the correctness of a solution obtained for a particular mathematical problem. Because using of mathematical programs to check the validity of the solution is an important step in scientific and engineering calculation, as it provides an additional level of verification and ensures that the solution obtained is accurate and reliable. Substitute typical values into the equation to ensure that the result is reasonable, that is within expectations. So it refers to the process of plugging in example values for the input and parameters of an equation or formula to verify that the output or result is plausible and falls within expected ranges. This method, commonly used in scientific and engineering calculations, to provide a quick check on the validity of the solution and identify potential errors or issues. Next is verify the boundary conditions for the independent parameters. Verify the boundary conditions for the independent parameter means checking the values of the independent variables or parameters to satisfy the parameters satisfy the conditions at the boundaries of the problem domain. Because verifying the boundary conditions for the independent parameters is an essential step in theoretical derivations and calculations. Next is make very slight changes to the material parameters used in the model to ensure that the results do not change significantly. It means testing the sensitivity of the solution to small variation in the material properties used in the model. Because testing the sensitivity of the solution to changes in material parameters is an essential step in theoretical derivation and calculation. It helps to identify potential sources of error or uncertainty in the model. Next is curve matching. There are many methods in order to verify the experimental data to scientific mathematical equations. One of it is to apply the independent variables to the equation and calculate the dependent variable. So if the equation remains true for the data, a plot of the calculated dependent variable versus the measured dependent variable should be a straight line. This plot's linear regression analysis will determine whether the result is statistically significant. So a visual inspection of the line will suggest the level of random error and data ranges where the relation fails. So unfortunately, systematic errors might result in this method of analysis being inconclusive. Such systematic errors include the possibility of an offset angle in a trigonometric function, example of a sinusoidal or cosinusoidal dependency. So it becomes necessary to estimate the value of this offset so that the curve is matched with least possible error. So consider the case of a polarized wave incident of a polarizing window. The radiation intensity detected on the other side of the polarizer should ideally be given to the equation. So this is the equation 3.1. This is the equation 3.2, where the offset angle of and the cross polarized component I1, I sub 1 must be determined using an optimization algorithm. The figure 3.6a, which is the raw data showing the variation in intensity with angle of the polarizer. And this is the B, the raw data plotted using equation 1. At 3.1, the best fit line is also shown. J sub O is equal to 1.55 watt per meter squared. Clearly, there is a systematic difference because an inspection by eye suggests that the data are not strongly linear, although the correlation coefficient is 0.9841. There is clearly systematic error as the deviation from a straight line is maximum in the center of the plot. Figure 3.6c, the variation in the line correlation coefficient plotted as a function of the offset angle. It shows the correlation coefficient varies as the offset angle is systematically changed in the equation. The best fit should occur when the linear correlation coefficient R is maximum, approximately equal to unity. And the last one, figure 3.6d, the raw data plotted using equation 3.2 with the best value of the offset angle. This occurs when the correlation coefficient is maximum. Strategically estimating the numbers until the root mean squared error RMS is minimized. The unknown values can be determined using a relatively straightforward method. The linear correlation coefficient R will be maximized in this situation. So that's all. So that's the end of the presentation. Thank you for listening.